So let's see. I want to remind you about where we left off yesterday. First, we had the point charge. I don't care. I can see it just fine. And clearly this is just the Mr. Shelton show, so it's all that matters with me. Not that we needed Gauss's law to do this, but the idea of using the Gauss's law gave us the actual meaning of Coulomb's constant. So, the equation for the point charge is simply what we already knew because we used Coulomb's law for that. But now we have a better understanding of where this comes from. And then we had a big divergence into talking about what, interesting variables or interesting constants are. Then we did the infinite line of charge. Has a charge density, not a total charge. So we have to switch over from dealing with a complete amount of charge, deal with the charge density. The electric field here had some kind of linear symmetry. That part's important because I'm not putting the direction of these electric fields here. I'm just putting an expression for the size of the electric field. And it decayed with distance away from the line. And it was just 1 over R. Slightly different thing going on here. It still is got K in it, but it's twice as big as K now. We think of it that way. But today, we're going to talk about the infinite sheet of charge. Oh, it's not Q. Lambda.
Yeah, I was going to say.
Lambda. Yep. Lambda. There we go. Bless you. Bless you. Okay. So you put all these things together, and we have the point charge, the infinite line, and the infinite sheet. These are the basic shapes that form all major capacitors. Parallel plate capacitors are 2 infinite sheets. Cylindrical capacitors are an infinite line. And we don't really make point charge capacitors. That's just too difficult to do. But they make up the basic shapes of how electric fields tend to be defined in all of our reality. So although there's other things, we use Gauss's law to create these 3 ideas about how the electric field dances around shapes. Now, Gauss's law is a lot to take in the first couple times. I don't want to minimize the fact that this is not easy to do, and sometimes it just feels like I'll have to take Mr. Shelton's word on it. There are situations where you're going to have to use this. You're going to have to execute on your own. Although we've done the 3 basic shapes, we've made the basic ideas of how we use Gauss's law in these cases, the truth is Gauss's law is of very little use to us outside of things that aren't symmetrical. So you'll notice all the things we've used are very symmetrical. A straight line that goes off in infinity, a straight big sheet that goes off in infinity. If there's anything asymmetrical about your shape, you can't use Gauss's law. And you will be asked that question on the exam. Can Gauss's law be used to determine the electric field in this circumstance? The answer will be yes or no, based on whether it's symmetrical or not. And it's always going to be about what kind of shape could you use in order to use Gauss's law. There's only going to be 3 possible shapes, probably only 2. It's a sphere or a cylinder or a box, and that's it. If there's any other shape that has to be used for your estimation of Gauss's law, it's likely you can't use Gauss's law. That's the important detail. We, in this class, have a limited amount of vocabulary when it comes to the shapes we can use. A limited amount of geometry that we can integrate through. So you've seen, at this point, 90% of what you can do with Gauss's law. There's just not enough else. Now, we are going to have other circumstances. And the very circumstance you have to be aware of is that Gauss's law allows us to see inside things in a way we couldn't look at before. This begins to border on the real, stuff that's actually out there. What if I had a sphere of charged gas? Like Jupiter, Saturn, Uranus, Neptune, the sun. A sphere of charged gas. A sphere of charged gas will have an electric field inside of it because there's charge all through it. Gauss's law can be used to determine the electric field both inside and outside. because Gauss's law allows us to determine the symmetry of our system. Consider this. I have a charged sphere. It has charge Q. It has radius capital R. Good to go? I want to determine the electric field, say, here, at this point, right there. It's outside the sphere. Now, a couple of weeks ago, we would have to talk about finding a box somewhere in my sphere, finding a way to describe this distance away from the box, its contribution to the electric field, and then do that for every single box on the sphere in 3 dimensions. Well outside of our abilities, outside of my abilities at least. I would not be able to do this problem, not easily. No, I couldn't do this problem, period. I'll be honest, there's just no way. I have forgotten so much, I just don't think there's a chance, but that's just it. This is where Gauss's law really shines. Would you agree the charged sphere is symmetrical? That there's a certain amount of symmetry I can exploit? Would you agree that the electric field this distance away, this distance r, is probably the same as the electric field the same distance away over here? Does that make reasonable sense? Because it's a sphere that if we're always the same distance away from the sphere, the electric field will also be the same. Does that make reasonable sense? Well, let's try using a spherical charge distribution, spherical Gaussian surface centered around my charged sphere. Is that okay? All right. To do this, we're going to use all the same things we talked about. We're going to talk about the charge enclosed and the flux. Something's going on. Now, I think the charge enclosed is easy. We all good with Q? We're enclosing the entire cloud. Of course, got to deal with the flux. I'm thinking we've got to do all of this. I don't have to break it up into more than one surface. It's one continuous sphere. So can we all agree that it's just going to be one surface? Yeah. Can we agree the electric field has probably got to be going that way through my surface? Can we agree that the area is in the same direction as the electric field? That gets rid of the dot product. Change that to cosine 0 degrees. Can we agree the electric field is the same everywhere on my sphere? As long as we are the same distance away from the cloud? Can we add up the area of the sphere? Put it all together? All I did was put in the area of the sphere, and then I went ahead and dropped in my constant, and I dropped in the charge. I'm seeing that the electric field around a sphere of charge is the same as a point charge. As long as I'm outside the sphere, it's as if the entire charge was at the center of the sphere. But I did it for a ball of gas. Still works, still the same. Yes, sir?
So does the arc of the actual gas cloud matter in this scenario?
Apparently not. Now, There probably is a situation where it would matter. What if instead I wanted the electric field inside the cloud? I think then something would matter here. But here's the thing, and don't make this harder than it has to be. Gauss's law is a law. It's invariant, which means that the only part of the charge that matters is the part that's inside the surface. It's how much charge is enclosed. Anything that's not enclosed doesn't matter. Don't need it at all. So if you can figure out how much charge is enclosed, you can figure out the electric field. Everything else is going to be the same. You do see that, right? If we don't care about anything outside that surface, then the electric field is still going to be going this way through the surface, because I only care about the charge inside. The area is going to be going this way through the surface. Why? Because that's the surface. It's based on where the enclosed space is. I do, though, need to figure out how much charge is inside my Gaussian surface. Yes, sir?
For the integral, that circle in the middle of the summation, if that circle, do we always have to put it, or like, can we what does that circle mean?
Okay, I'm going to ask you to do me a favor. So you're talking about right here, this little circle right there.
Yeah.
It means that the surface that I use, the Gaussian surface that I choose to use, has to be completely closed. There can be no holes in it, no openings in it, no gaps in it. Does that make sense?
Yeah.
So my Gaussian surface couldn't be a cup, because a cup has an opening at the top. It can be a cylinder. It can't be a hemisphere, but it can be a sphere. Does that make sense?
Yeah.
Because basically I have to add up all of the possible electric field that could be coming from inside my sphere. So I want to do this problem because it looks super, super complicated, but ultimately it can't possibly be any more difficult than what we've just done if you can tell me how much charge is inside that circle. In fact, here's what I'm going to do. I'm going to go to another page to clean it all up, to make you do this part so that's not me doing it. The whole sphere has radius capital R. My little bitty sphere, my Gaussian surface, has radius little r, but the whole sphere has charge Q. Can you tell me, just using what's on the board right now, you'll need nothing else, what the charge is inside the little sphere? Think ratios. Think ratios. Try it. It gets you to do this, but density in this case is charge per unit volume. So the charge per unit volume for the whole sphere has to be the same for the charge per unit volume of the little sphere. Write that out. Write that thing I just said out, and you have the answer.
I thought it was.
I'll just say it again. The charge per unit volume of the big sphere has to be equal to the charge per unit volume of the little sphere. That has to be true if the charge densities are the same. If you write that out, you have the answer. That tells me if you're listening or not. Charge. Oh, you need to know the volume of a sphere. I know I didn't give it to you. I expect you to bring something to the table. If you don't know the volume of a sphere, you can be forgiven. This time. There will be a next time, and if you forget it next time, there will be no forgiveness, no place you can go where we won't laugh at you. 4/3 pi r cubed. I'm going to put Q enclosed because that's what we're looking for, right? But Mr. Sheldon, you said we couldn't use anything else but what was written on the board. I know, and I mean it. Right? Cancels out. So Q enclosed, that's the ratio. That's how much charge has to be inside the little sphere. It's based on the cube. It shouldn't surprise you that's based on the cube. Cubes are, volumes. Squares would be areas, and lengths would be similar. So I enclosed a little sphere in my big sphere. The ratio of the volumes has to be the ratio of the cubes of the radii. Now, either way, you're really quite done. Because the other side of this was to do E dot dA, which we've already done. Every other part of this is exactly the same. Dot product is the electric field in the same direction as the area for the little sphere. Yes, it is. Is the electric field uniform everywhere on the surface of the little sphere? Okay. Oops, not equals. Can you add up the entire area of a sphere? Make sure you use the right R here. You will screw this up. This is little r. Can you drop this back in place? In Gauss's law? I can. Can you? I put Q enclosed there, dropped in my little epsilon naught. I see there's an r squared on the right side and an r cubed on the left side. I think we're going to see some things cancel out. Do you see that too? So running short on space here. I think we're going to see the electric field. And I see a 1 over 4 pi epsilon naught. Let's get that out of the way now. And I'm going to have one little r left on the top and 3 r's left on the bottom. Because 2 of the r's canceled. Right, the r squared canceled with the r cubed. Interesting point here. First, check this. You can check this. What do you think the electric field should be in the very middle? If you were standing in the middle of this sphere, charge all around you, wouldn't you be pulled equally in all directions? So what would you expect the electric field to be in the center?
0.
Does this electric field go to 0 when R equals 0? Sure does. We also know that outside the sphere, it looks like a point charge. So what happens to the electric field when R goes to capital R? Does it become a point charge? Sure does. This is actually the electric field inside a charged sphere. We have charged spheres all the time. We call them atoms. An atom is a ball of charge. It has a strong positive at the center and a cloud of negative around the outside that's relatively uniformly distributed. This is a real thing. And the electric field inside an atom behaves a lot like this. Notice it's linear. The electric field builds in a linear way. It's proportional to R. Everything here, and this is the kind of thing that really changes E&M mechanics. If you group everything that stays constant in this equation, it's there. And all those things are constants. They are part of the entire thing from the very beginning. Big R is the radius of the whole sphere. Big Q is the charge of the whole sphere. 4 pi epsilon. Those are all constants. This is a linear equation. If you were asked to graph the electric field as you start from the center and go away, for a large part of it, The electric field would just be a straight line because it's linear until you make it to the edge. Then when you make it to the edge, is it linear still? Nope. Because as soon as you make it to the edge, we have the other formula that we also proved. There, r squared, so it goes like that. Linear on the way up, and then over r squared on the way back. Believe it or not. So to kind of get that out there, I said I need to draw something that looks like a sheet. I'm still not convinced that this looks like a sheet, but I don't really know what else to do.
Can you go back one slide with the summary you were doing?
So we said that this is going to have a charge density sigma, and we use sigma as coulombs per meter squared. So it's a surface charge density. It's taking that charge and spreading it uniformly about the surface. And we're saying for the time being that this surface is, infinitely thin. And I think we also had a certain amount of discussion about the fact that the electric field itself is kind of extended outwards away from the sheet. And it's hard to draw it because it's, we're trying to make it somewhat 3D here, but the electric field itself is going to have this uniformity to it, which suggests the kind of shape we want to use for our Gaussian surface. And again, if I did not make this part clear, I need to really identify that the Gaussian surface is a fictitious surface we make up for the purpose of using Gauss's law. It has to be a 3D, completely enclosed and bounded shape. And yesterday we decided we would use I believe a box. Is that what we decided? So we're going to have, that's not a box. We're going to have a box as our shape. And I had to make sure, and I want to reiterate it, that we place the box so that it is symmetrical, in place so that half of it's on one side and half of it's on the other. I've always been told to use a cylinder and turn it on its side, but it does not matter whether we use a box or a cylinder. The only real difference between using a box or a cylinder is that if we use a box, we have to test all 6 sides. And 4 of those sides have been divided in half. So that really makes, 8 plus 2, 10 sides. If we use a cylinder, then there's 3 sides and only one of them is cut in half. So it ends up being 4 sides to test. So the difference would be that our cylinder would look something like this. And the other half would appear on the other side of this sheet. Do you follow the difference? But it doesn't matter whether we use a squared off box or we use a cylinder. I hope you recognize the only surface that's going to matter is the top and bottom of the box or the cylinder. Because if we do this right, these electric field lines that are coming off of the surface are not going to in any way go through the side portions of the box. So if I say that this is a side, this part here, and this is the bottom or top, none of the sides should have any electric fields that penetrate or pass through the sides. They will not contribute to the electric flux. Now, you guys tend to not write down those kinds of things, but then you ask me questions about it later. So here's where I pause and say, I don't want to answer this question later. I'm going to try and put my shape, whether it's a box or a cylinder, I'm going to try and put it in such a way that these parallel field lines that are coming out of the sheet don't pass through the sides of the box or the cylinder. And that the only part of the flux that will contribute will be the field lines that pass through the top or the field lines that pass through the bottom. Is that okay? Go ahead. Yes. For the last time. I'm going to position the cylinder or the box in such a way that the field lines don't pass through the sides of that box, but only pass through the top or bottom. This has the effect of meaning the only field lines that contribute to the flux are the ones through the top and the bottom. I mean, if we look just in this picture here, I keep moving stuff around, but what I'm really trying to do is make sure that the sides of our shape are perpendicular to the sheet. This way those field lines can't pass through the sides. Because ultimately, I'm still going to have to deal with the fact that there are two sides to Gauss's law. There's the enclosed charge, and there's the electric flux. Now, the enclosed charge is going to be whatever amount of charge is trapped inside the box. Now, remember, this is in, sigma is in coulombs per square meter. So what we really need to figure out is what is the area of the top or bottom of our box. And I'm not going to make this hard. It doesn't matter. I just need to know what the area is. I'm going to say that this has area A. I know I could do pi r squared or side times side, but I don't really need to. You'll probably come to grips with the idea that eventually I'm going to be looking for the amount of flux, and it's going to also involve this area. So rather than using pi r squared or side times side, I'm just going to say that the amount of enclosed charge is sigma times the area of the top, or the area of the bottom, because the area of the top and the area of the bottom have to be the same. It's a uniform shape. So if it's a cylinder, the top and bottom are the same. If it's a cube, the top and bottom are the same. Everybody okay so far? Make sure, before I go on, this is how much enclosed charge there is. Now the flux. The flux is going to be more difficult for me to deal with. I've got to deal with, that more complicated calculation. So let's consider the flux. Let's move this over here so I can kind of get this by itself for a moment and talk about flux. Flux is this integral of E dot dA. When I look at this, I recognize that there's really three separate integrals that I have to add together here. There's going to be the integral of the top. I'm going to add to that the integral of the bottom. And finally, although there's a lot of them, I'm going to put the integral of the sides at the end. Because the thing that's important about the sides is that they all contribute nothing to the flux. And when we look at the picture, the contribution is a combination of the amount of electric field that passes through that area and how big the area is, and a comparison of the direction of the area and the direction of the electric field. Those three things we have to look at: the strength of the electric field, the area that that electric field passes through, and the direction between the area and the electric field. On the sides, the direction of the area has to be away from the center, but is clearly going to be perpendicular to the electric field. Same with this side. Same with the side that faces us. all of these cases, the area is perpendicular to the electric field. That makes their dot product 0. So all of these cancel out. No electric field passes through the sides. The bottom and top both are going to contribute, and it's important to recognize they both contribute in a positive way. They add flux because the electric field is aligned with the area on both the top and the bottom. Everybody okay with that so far? So I've dealt with the dot product here. I know it's going to be the cosine of 0 degrees for both. Dot product is cosine, and the area and the electric field point in the same direction, so 0 degrees. That makes this E times dA for the top plus E times dA for the bottom. And I'm going to ignore the cosine of 0 degrees because it's just 1. Next, I've arranged this purposefully so that the electric field is constant everywhere along the top because it's the same distance away from the sheet. Is that okay? I did more than that though. I centered my shape so that the top was the same distance away from the sheet as the bottom was. This is important because I want to say that the electric field contribution at the top and the electric field contribution at the bottom are the same amount, even though I'm pulling them out of their respective integrals. What I'm saying is I'm going to pull the electric field out, but if I made sure that my shape was balanced, then the amount of the electric field that's here should be the same as the amount of electric field that's here. Which means I don't have to subscript these. They are the same value for electric field. So everybody understand what I'm saying? I'm trying to be very diplomatic, very careful, very slow. I'm also making sure to go through all of the steps necessary to utilize Gauss's law. I hope that you are taking the time to fill in how I went from here to here. Did you write down what you have to do to go from there to there? I separated the integral for each face of the shape that I used. So separate sums. I mean, it's nice if you have all this written, but when we're done, all you have is a page full of weird-looking S's and nothing to tell you what you did. And then again, you later on, you go, I don't know what we did in class today. I need you to stay with that so you have something there, instructions. So I take my big integral and I break it up for each of the sections of my shape. I then evaluated all the dot products. I went to each shape and looked specifically at the direction of the area compared with the direction of the electric field. I dealt with the dot products. I compared the direction of the areas with the direction to the electric field. It's probably a little presumptuous to say this, but we had to guess at what we thought the electric field looked like. Right? That whole story about, I think the electric field lines are all going to be parallel. I'm guessing. I think it's true. It makes sense to me because of its uniformity and symmetry. But yeah, you're having to guess that. You wouldn't know that ahead of time. You're just looking at the symmetry and thinking, I can't imagine the electric field wouldn't be this way. But at the same time, you guys are seeing this for the first time. So there's no reason for you to believe that, except that you have to take my word on it. But doesn't it seem to make sense? If it was uniform, then we'd have uniformity of the electric field lines. Here, we eliminated the parts that didn't contribute to the problem. The places where there was no contribution to the flux. No electric field pierced the area. Here is where we're deciding if the electric field changes over the area. That's an important step that so far we've really not spent any time on. We have always carefully decided that our shape would be such that the electric field would be the same on every part of the surface compared to the area. Meaning every piece of the area had the same amount of electric field passing through it. This was going to leave us with a summation that's not really a summation. It's saying add up all of the area. So that makes this the area of the top, and this the area of the bottom. So actually executing our summation, if we do this right and we're very careful, the execution of our summation is just to put the area there. And I don't have anything else but A. I didn't make it a specific shape. And not because I'm trying to confuse you, because it won't matter. You'll notice, as long as the area of the top and the area of the bottom are the same, then I don't need to subscript them. If it's a cylinder, the top and bottom are the same. If it's a square, the top and bottom are the same. Giving me a total electric flux of E times A, where this represents, 2E times A. This is the area of the bottom or top. Now, part of the reason why I did it this way is because when I come back over here, it's the same area that determined how much charge there was. Right? The area of the top or the bottom is the same area. So we cancel out those areas. And you'll notice the length in the cylinder yesterday, it canceled out. This is canceling out too. Doesn't matter how big our surface is or how much of the sheet we take in, we believe the electric field is going to be similar everywhere. Solve this for the electric field, and we get sigma over 2 epsilon naught, which I hope all of you notice is a constant. Right? Doesn't depend on how far away you are from the sheet. The electric field is the same everywhere near a sheet. It's a constant. How do you make a uniform electric field? You charge up a sheet of charge. It creates a uniform electric field. In your notes, a big box is probably a good idea there. A sheet of charge has a uniform electric field that emanates in both directions away from it. Now, it's hard to make an infinite sheet of charge. It is not hard to make a sheet of charge and get close to it. So an infinite sheet of charge is just any sheet of charge if you're close enough to it. That's how you make a uniform electric field, is a sheet of charge. Yes, sir?
Can you repeat the sentence about the sheet charge of the uniform electric field pointing both ways? Is that what you said?
Yes. The electric field points in both directions away from the sheet. So there's and that is important. The electric field is emanating in both directions. That's what produces this 2 here. That's a little critical because we're going to talk about that 2 in a little bit.